Put a cup of hot coffee right in front of you. Just place it on the table and look at it. What do you see? The liquid seems calm. It might wobble slightly if the table is unstable, but overall, it looks motionless. A smooth, dark surface, silence, stillness. And here lies the greatest deception that your eyes impose on your brain every single moment of your life. Because if I could give you glasses right now that amplified your vision 1 billion times, you would recoil in horror from this table. What you call a quiet cup of coffee is actually a raging hurricane. It is a planetary scale catastrophe trapped in porcelain. There is no rest there. There is no smooth surface. There are billions and billions of tiny balls bashing against each other, shoving, bouncing, and spinning in a mad dance. They never stop, not for a second. And when you take a thermometer and dip it into this cup, you think you are measuring some property of the water. You say, oh, the temperature is 90 degrees, as if 90 is a color or a taste, as if it is something contained inside the water. But it isn't. Temperature as a physical entity does not exist. Let me explain. For a long time, people, even very smart scientists, thought that heat was an invisible fluid. They called it caloric. They believed that when you heat a stone, you pour this fluid into it and it swells. And when the stone cools down, the fluid flows out. Sounds logical, right? But it is complete nonsense. There is no fluid. There is no hotness that can be poured in or out. There is only motion. The entire difference between boiling water capable of cooking an egg and a block of ice capable of freezing a finger lies not in what they are made of. They are made of exactly the same water molecules. The difference is only one thing: speed. In hot coffee, the molecules are crazy racers. They rush around at breakneck speeds, crashing into each other, bouncing off the walls of the cup. Bam, bam, bam. Billions of impacts per nanosecond. In cold lemonade, those same molecules are tired old men. They move too, they shove too, but they do it lazily. They just wobble from side to side, slightly nudging their neighbors. The thermometer you dip into the water doesn't feel heat. It feels punches. The glass of the thermometer is being bombarded. If the water molecules hit it hard and often, the mercury crawls up. If they hit weakly and rarely, the mercury crawls down. A thermometer is not a magic sensor. It is a speedometer. It measures how hard the matter around it is shaking. Think about this for a second. Right now, the air in this room is bombarding your skin. Nitrogen and oxygen molecules are crashing into your cheeks at the speed of a bullet. Literally hundreds of meters per second. You don't feel this as impacts only because there are too many of them and they are too small. You feel it as steady pressure and warmth. But if we could stop this dance, if we could order every atom in this room to freeze in place, do you know what would happen? The air would stop pushing. It would collapse to the floor in a pile of dust. Temperature would vanish. Sound would vanish. Life would vanish. Because life, heat, everything we perceive, is a side effect of the fact that the universe cannot sit still. It trembles. It shakes. It has, if you will, a nervous tick that never goes away. In physics, we call this kinetic energy, but I prefer to call it the great jiggling, or simply put, jigga jigga. And the most amazing thing here is not just that they move. The most amazing thing is how exactly this movement creates all those strange effects we see every day. Why does steam burn? Why does ice melt? Why does metal expand? To understand this, we need to stop looking at the world with our giant, clumsy human eyes. We need to shrink. We need to go down there into the thick of the fight. To a place where there is no up, no down, no warm, no cold. There is only endless collision. And right now, I invite you to dive into this chaos. Imagine a situation. Let's say some terrible global catastrophe occurs. All our accumulated knowledge is destroyed. Libraries burn, servers melt, scientists disappear, and we have the opportunity to pass on only one phrase to the next generation of survivors. One single sentence that contains the most information about how our world works. Which phrase would we choose? I am convinced it must be the atomic hypothesis, or, if you like, the atomic fact. It goes like this. All things are made of atoms, little particles that move around in perpetual motion. attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In this one sentence lies all of physics, all of chemistry, and all of biology. If only you have a little imagination and the ability to think. Let's look at this through our imaginary microscope. Take a drop of water, magnify it millions of times. At first, we see all sorts of paramecia, but we aren't interested in that. Magnify it even more. And now we see something resembling a crowd of people in a stadium, seen from a helicopter. Lots of little blobs shoving and rubbing against each other. These are water molecules. Hydrogen, oxygen, you know the story. But look at how they behave. In liquid water, they are slippery. They press against each other. They like being together, but they don't hold hands tightly. They constantly switch places, squeezing past neighbors. That is exactly why water flows. That is exactly why you can dip your finger into it. The molecules simply part ways to let you through. But what happens when we take energy away from them? When we cool the water? Remember, temperature is the speed of motion. We start taking speed away from them. The movement slows down. The jigga becomes sluggish. And at some point, the attraction between them defeats the chaos. They lock together. They line up in a rigid structure. Click, click, click. Suddenly they can no longer wander wherever they please. Each atom takes its designated place in a crystal lattice. We call this ice. But here is what boggles the mind. Even in solid ice, even in a chunk of granite, even in a diamond, the atoms do not stand still. Never. Look at an ice cube. It seems dead, frozen, cold. But inside this cold block, an earthquake is happening that would tear us apart if we were the size of an atom. Each atom of ice is like an angry dog on a chain. It has its place, its doghouse, and it cannot run away as it could in water, but it jerks. It vibrates in its place. Left, right, up, down. It slams against the invisible walls of its cage, and the warmer the ice is, while it hasn't melted yet, the longer this chain is, and the more furiously the dog thrashes. Now let's do the reverse. Let's heat this ice. We start kicking these atoms, adding energy to them. They start shaking harder. The amplitude grows, and at some point the shaking becomes so violent that the chain cannot hold. It snaps. The dog breaks loose. The structure collapses. The ice melts. The atoms are once again walking freely, shoving and sliding. We continue to heat. We give them even more speed. Now some of them are moving so fast that even the attraction of their neighbors cannot hold them back. They accelerate and bam, fly right off the surface of the water. They fly into the air, free and alone. They scatter in all directions, crashing into walls, into the ceiling, into your face. We call this steam or gas. Gas is total anarchy. In a solid, there was a dictatorship of order. In a liquid, there was a democracy of the crowd. In a gas, complete chaos. Molecules rush around like madmen, huge distances between them, impacts of terrible force. And here's the key point to understand. When you feel the pressure of steam, for example, in a pot lid that is jumping up and down, it is not some continuous force. It is billions of tiny punches, as if you were throwing tennis balls at a wall. If you throw enough balls fast enough, the wall will feel constant pressure. So when you look at the world around you, at the table you're sitting at the air you're breathing, at your own body, you shouldn't see static forms. You should see a dynamic, vibrating swarm. Nothing stands still. Everything shivers. And the intensity of this shivering determines whether an object will be solid, liquid, or if it will evaporate into oblivion. We live in a world that shakes, and what we call the solidity of matter is simply the balance between their desire to cling to each other and their mad desire to move. But there is another question. If they are just shaking, why does it hurt? Why, when this movement becomes too fast, does my hand feel a burn? How does motion turn into pain? Let's go back to that moment when you accidentally touched a hot frying pan. It happens in a fraction of a second. You pull your hand back, you might scream, and your finger throbs with pain. In school, you might have been told, heat transferred from the pan to the finger. It sounds so nice and harmless, as if the pan gave you a gift, as if heat is some substance, like honey, that flowed from one object to another. But if you look at this from the atom's perspective, you won't see a gift. You'll see a brutal bar fight. You'll see a beating. Here is your pan. Its iron atoms are revved up by the stove's fire. They are heavy, massive, and incredibly fast. They vibrate with wild amplitude. They are like enraged heavyweight boxers swinging their fists in all directions without looking. And here approaches your finger. The atoms of your skin, proteins and water inside your cells, they are relaxed. They have a comfortable temperature of 98.6. They move, but smoothly, in a waltz rhythm. They suspect nothing. And then contact happens. The boundary between metal and skin disappears. A fast, heavy iron atom slams into a slow, light skin atom with full force. Bam! This is pure mechanics, like a truck smashing into a parked car at full speed. What happens at collision? Conservation of momentum. The iron atom slows down a bit. It gave away some of its energy. But the skin atom? It flies off with insane speed. It took a hit so hard that it starts thrashing in panic. But the nightmare doesn't end there. This victim atom of your skin has now become a projectile itself. It crashes into its neighbor, a molecule deeper inside your finger, and passes the punch to it. That one hits the next one. It is a chain reaction of violence. A wave of punches propagates deep into your body. Billions of molecules start shaking chaotically, tearing bonds, breaking protein structures. This is exactly what a burn is. A burn is not too much heat. A burn is when your own atoms start moving so fast that they tear themselves apart. And what is pain? Pain is just a signal. Your nerve endings are also made of atoms. When the shaking reaches them, they start vibrating at a dangerous frequency, and they send an electrical impulse to the brain. The decoding of this impulse reads, "Hey, down here, the movement has become too fast. The structure is collapsing. Do something. Get us out of here." Your brain interprets this message of high kinetic energy as the sensation of hot and pain. Now think about the opposite situation. You touch a piece of ice, and you feel cold. What is happening? Is cold flowing into you? No. In nature, there is no such thing as cold. Cold is simply the absence of motion. When you touch ice, the same boxing match occurs, but now the heavyweight is you. Your finger's atoms are fast. The ice's atoms are slow. Your atoms punch the ice, rocking it, causing the ice to melt. But with every punch, your atoms lose speed. They slow down, they calm down. The jigga-jigga quiets, and the nerve endings send a telegram again. "Attention! We are stopping. We are losing speed. Motion is freezing." The brain translates this as cold. Do you see where I'm going? In the universe, there is no hot and cold as two different paints. There is only motion and its transfer. When you sit in a room, air molecules are constantly bombarding your skin. If they hit harder than your own atoms shake, you warm up. If they hit softer, you cool down, giving them your energy. You are constantly in a state of exchanging blows with the environment. You are never isolated. It is an endless game of billiards. Trillions of balls collide every nanosecond. And everything we call thermodynamics is just an attempt to keep score in this game. Who hit whom? Who sped up? Who slowed down? But there is a trick here. One detail that confuses even physics students. If I put a hot spoon on the table, it cools down. Its fast atoms pass energy to the table and the air. They calm down. The average speed drops. But does that mean all the atoms of the spoon slow down? No. And this is where the magic of statistics begins. Because in a crowd, there are always those who break the rules. When we say the water temperature in a glass is 68 degrees, we are lying brazenly. We simplify reality down to a single number. It seems to us that if the temperature is room temperature, then all molecules in the room are behaving decently and moderately, like soldiers marching at the same speed. But nature hates marching. Nature is not an army. Nature is a party that has gotten out of hand. Recall that billiards game we talked about. Imagine two balls colliding, two atoms. Let's say they are both flying at average speed, but the impact happens at a tricky angle. One ball takes a glancing blow and almost stops. Where did its energy go? It didn't disappear. It went to the second ball. And now this second ball is flying twice as fast. And then this fast guy crashes into someone else and maybe steals even more energy. As a result of random, chaotic collisions occurring billions of times a second, speed is redistributed in the most bizarre ways. This is called the Maxwell distribution. Sounds boring, but actually it is a graph of chaos. In any glass of water, even the coldest one, there is always a majority, the middle class. Molecules moving at normal speed. They are what define what we call temperature. But always, absolutely always, there are the outliers. There are the slow guys. Molecules that accidentally lost almost all their energy in collisions and are barely crawling. And there are the psychopaths. Molecules that were incredibly lucky, or unlucky, to receive a series of accelerating kicks. They rush inside the glass at speeds many times higher than the average. And here is a fact that might make you look over your shoulder nervously. Right now, in the air right in front of your nose, in this quiet and calm room, there are nitrogen molecules moving at the speed of a pistol bullet, 500, 600 meters per second, right into your face. You are lucky they don't kill you. Do you know why? Only because they are incredibly light. They have huge speed, but tiny mass. Their kinetic energy is just enough to create microscopic pressure on the skin, not to punch a hole in it. But if a nitrogen molecule weighed as much as a bullet, you would be dead already. So temperature is just statistics. It is the average temperature of patients in a hospital. But it is these rare, fast molecules, these psychopaths at the tail end of the graph, that do the most interesting things in the universe. Chemical reactions? They happen only thanks to fast molecules. To start a reaction, you need to smash atoms against each other hard. Average molecules just bounce off. Only the fast ones shatter and combine into something new. Life exists only because in the warm soup there is always someone fast enough to kickstart the process of change. This completely changes the view of things, right? Looking at a glass of water, you now understand. Not everything is calm in there. There is a lottery going on. Every fraction of a second, molecules exchange speed. Someone wins the jackpot and becomes super fast. Someone goes bankrupt and freezes. And this leads us to a puzzle. If there are super fast molecules in a glass of water rushing around like mad, what stops them from just flying out of the glass? What stops them from tearing through the water's surface and escaping into the atmosphere? The answer is simple. Nothing stops them. They are doing it right now. And this process of escape explains one of the most familiar miracles you encounter every time you drink tea. Let's go back to that spoon of hot soup. You bring it to your lips, feel the heat, and instinctively do what every child and adult on earth does. You blow on it, and the soup cools down. But why? Many think, well, my breath is colder than the soup, the air mixes with the water and it cools down. This plays a role, but a tiny one. And if you blew on the soup with a hot hairdryer, it would also cool down, though it would dry out eventually. The main reason lies in those crazy fast molecules we just talked about. Look at the surface of the water in the spoon. For a water molecule, this is the edge of the world. Below are friends and neighbors pulling it back, holding hands, not letting go. Above is air, a frightening void. To break free from the liquid captivity into the air, a molecule needs to perform work. It needs to tear bonds with its neighbors. This requires huge energy. The average molecules don't have this energy. They jump up, get pulled back, and fall back into the soup. But remember our psychopaths, molecules with extremely high speed. They rush upwards, slam into the surface, and they have enough power to overcome the neighbor's attraction. Snap! The bond is broken. The molecule flies out into the air and becomes vapor. It escaped. Now watch my hands. This is pure arithmetic. Imagine a city inhabited by people with different incomes. There are poor people, a middle class, and billionaires. The average income in the city is, say, $50,000. Now imagine that all the billionaires suddenly packed their suitcases and left the city. What happens to the average income of the remaining residents? It drops sharply. The same thing happens in a cup of coffee. Only the fastest ones fly away, only the hottest ones. They take with them the lion's share of kinetic energy. And who remains? The slow, sluggish, cold molecules remain. Since temperature is the average speed, by removing the fast ones, we lower the temperature of the entire liquid. That is what evaporation is. It is a process of selecting the best and banishing them. Water cools because it loses its most energetic particles. So why do we blow? You see, the molecules that flew out don't immediately fly into space. They hang over the cup, forming a cloud of vapor. And sometimes they crash into air molecules, bounce back, and plop right back into the coffee, returning their energy. These are returnees. They hinder cooling. When you blow, you sweep this cloud away. You say, "You escaped, so stay gone, don't come back." You clear the space for new fugitives. You constantly remove the fastest ones, allowing the next fastest ones to take their place and fly away too. It is a conveyor belt for removing energy. And nature, of course, thought of this billions of years before we invented soup. Look at your skin. Why do we sweat when we are hot? Or when we run? Your body is a biological machine, and when it works, it heats up. Atoms inside you start shaking too much, threatening to destroy proteins. The organism urgently needs to dump excess jigga. It throws water onto the surface of the skin and tells this water, "Run, save yourselves." For a sweat molecule to evaporate, it must get energy for the jump from somewhere. Where does it get it? From your skin. It steals a massive dose of heat from your body, uses it as fuel for acceleration, and flies off into the atmosphere. You feel coolness not because the water is cold, but because every evaporated molecule took a tiny piece of your heat with it. You are literally paying with water to calm your atoms down. It is a brilliant system. We use chaos to control chaos. But wait, if we learn to understand how molecular motion creates pressure, remember the balls hitting the wall, and how heat forces them to scatter, maybe we can force this chaos to do something useful? Not just cool soup, but move mountains? Up to this point, we let our molecules do whatever they wanted. They danced, they evaporated, they flew into the sky. But humanity didn't build civilization just by watching steam over soup. We built civilization when we decided to lock this beast in a cage. Imagine we take the same water, heat it, force the molecules to go berserk, but instead of letting them fly away, we cover the pot with a heavy lid and weld it shut tight. What happens inside? Hell breaks loose. Molecules accelerate to insane speeds. They want to break out, but they can't. They slam into the vessel walls. Bam, bam, bam. Trillions of blows. And since we keep heating them, they hit harder and more often. All this furious, chaotic energy, all this disorderly thrashing seeks an exit. And if we make one wall of this cage movable, let's call it a piston, a miracle happens. Billions of microscopic punches merge into a single, powerful force that pushes the piston up. Think about what we just did. This is the most important trick in the history of technology. We took chaos, disorderly motion in all directions, and turned it into order, into motion in one direction. We forced chaotic heat to do useful work. That is exactly how a steam locomotive works. That is exactly how power plants, working to light up your homes, function. Somewhere out there, far away, coal is burning, or uranium is splitting to heat water, to anger molecules, so they start beating against turbine blades. And when you drive your car down the highway, the same thing happens, only even more aggressively. Your car engine works only because billions of small gas molecules are furiously beating against metal. Inside the cylinder, an explosion of gasoline occurs. What is an explosion? It is an instant, catastrophic release of heat. In a fraction of a second, the temperature jumps to thousands of degrees. Gas molecules that were calm a second ago suddenly get a kick so hard they start flying at supersonic speeds. They are cramped. They are in pain. They panic and look for a way out. They hammer the piston with such fury that a multi-ton machine tears off from its spot. You don't drive on gasoline, you drive on bombardment. You drive on the fact that hot gas hates being trapped. It seems like we won. We learned to control heat. We are kings of nature. We can take any energy and turn it into motion, right? Not quite. And this is where the most depressing law of physics comes into play. You see, turning work into heat is very easy. Rub your palms together. Feel it? You performed motion, and it turned into heat. 100% of your work went into heating. Simple. Breaking is easier than building. Creating chaos from order is elementary. But doing the reverse, turning heat back into work, here nature trips us up. Imagine you're trying to organize a crowd of frightened people running in panic in different directions and force them to march in formation. You can direct part of the crowd into the right channel, but you will never, do you hear me, never force everyone to run perfectly evenly. Someone will trip, someone will run the wrong way, someone will just stand still. In an engine, we can never take all their energy from the molecules. Part of the heat is always lost. The exhaust pipe is hot. The radiator is hot. This is the tax we pay to the universe for using its energy. This is the chaos we've failed to tame. And this is not an engineering problem. We can't just build a better engine. It is a fundamental law of the universe. Heat is a very low grade of energy. It is garbage energy. And when you turn something useful into heat, bringing it back entirely is impossible. We call this the arrow of time. You can break an egg and make an omelet, but you cannot turn the ground meat back and make an egg. Why? Why does nature love a mess so much? Why does hot always cool down and cold never heats up by itself? The answer lies in one scary word that frightens even physicists. Entropy. Imagine you're watching a movie. In the shot, a man jumps into a pool. Splashes fly in all directions. Everything is normal. Now imagine the film is played backward. You will notice it immediately. You will see splashes gathering from the water, merging into a perfect stream, and pushing the man dry onto the diving board. You will laugh because you know, in reality, this doesn't happen. But why? If you look at the collision of two individual atoms and play that movie backward, you won't see a difference. The laws of physics work the same way in both directions for two atoms. One hit the other, they flew apart. Play it back. They approached, hit, flew apart. No rules broken. But if the laws of physics are reversible for atoms, why are they irreversible for a pool of water? Why do we never see a broken cup assemble itself from shards? Why does heat always flow from hot to cold, and never the other way around? Welcome to the world of entropy, or as I like to call it, the curse of shuffling. Imagine we have a box divided by a partition. In the left half, gas molecules painted blue. Let's say it's cold gas. In the right, red molecules, hot gas. Everything is neat. The order is perfect. Now we remove the partition. What happens? The molecules start moving. Blues fly right, reds fly left. They collide. They shove. In an hour, you won't have a red and a blue half. You will have a uniformly purple gas. Warm and cold mixed and became just warm. Now ask yourself a question. What is the probability that if we wait another hour, a year, a century, all the blue molecules will suddenly randomly decide to gather again on the left, and the red ones on the right? Theoretically, it is possible. Atoms move randomly. There is no law forbidding them from returning to their starting positions. But practically, the probability is so small that the lifespan of the universe wouldn't be enough for you to wait for such an event, even in a thimble of gas. You see, there is only one way to arrange the molecules so that there is order, all blues on the left. But there are trillions of ways to mix them up. Nature isn't evil. She doesn't want to purposely ruin your hot coffee or turn your order into chaos. Nature is just a blind dealer in a casino who endlessly shuffles the deck. And since there are billions of times more disorder options than order options, we always move toward disorder. This is entropy. It is a measure of how much everything is mixed up. And this explains why heat is irreversible. Heat is chaotic motion. When you break a car, the orderly rotation of wheels turns into the chaotic trembling of atoms in the brake pads. You turned work into heat, you created chaos. Gather that chaos back, force all the pad atoms to hit in one direction simultaneously to spin the wheel. Good luck. The odds are 0. This is a sad truth. The universe is constantly moving from order to disorder, from batteries to dead batteries, from hot stars to cold vacuum, from hot coffee to room temperature. We are all moving toward a state where everything will mix, everything will become the same temperature, and nothing interesting will ever happen again. No energy will be transferred because there will be no one to transfer it to. Everyone will be equal. And this is called the heat death of the universe, a giant puddle of warm, boring sludge. But don't rush into depression. We aren't there yet. We live in an era where temperature differences are huge, and it is this difference that gives us life. And since we are talking about extremes, if the universe tends to cool down, calm down, and freeze, let's see if this process has a limit. What is at the very bottom of the temperature scale? Let's conduct a thought experiment. Let's start taking energy away from atoms. We will cool them more and more. First, water turns into ice. Then carbon dioxide turns into dry ice. If we go lower, minus 196 degrees Celsius, the air in this room becomes liquid, like water. At minus 210, nitrogen freezes into solid white blocks. But we go further, we descend into the depths of cold, where all familiar chemistry stops. Minus 250, minus 270. Logic tells us, if temperature is motion, then there is a limit. There must be a point where motion stops completely, a full stop, the death of motion. Scientists call this absolute zero, minus 273.15 degrees Celsius, or 0 Kelvin. In the classical view, if we reach this point, atoms should freeze in their places like soldiers standing at attention. No vibration, perfect order. Crystal, dead silence. But here's the catch. Nature hates zero just as much as she hates infinity. When we approached this limit in laboratories, and we got incredibly close, down to billionths of a degree, we discovered something strange. We discovered that atoms refuse to stop. Why? Because of quantum mechanics. You see, in the quantum world, there is a rule that cannot be broken, the uncertainty principle. Roughly speaking, it states, you cannot simultaneously know where a particle is and how fast it is moving. You must choose. The more precisely you know the position, the less you know about the speed. Now imagine an atom at absolute zero. If it stopped completely, we know its speed. It is zero. And we know its position. It is standing right here. We know both with perfect precision. And nature says, no, that is forbidden. Therefore, no matter how much you cool a substance, atoms never freeze completely. Even at absolute zero, 0-point energy remains in them. It is a tiny, ghostly trembling, a quantum itch that cannot be scratched. The atom sort of smears out in space. It is a little bit here, but a little bit there too. It vibrates not because neighbors push it, but because its very existence requires motion. This is astounding. Even if you remove all heat sources in the universe, if you extinguish all stars and wait trillions of years, matter will still shiver. The clearest example of this rebellion is helium. Helium is a noble gas, a loner. At normal pressure, even if you cool it to absolute zero, it will never become solid ice. It will remain a liquid. Why? Because this 0-point trembling of its atoms is so strong that they cannot lock into a crystal lattice. Quantum mechanics literally prevents helium from freezing. To turn it into a solid, you have to apply huge pressure to forcibly crush this quantum dance. So absolute zero is, in essence, a ghost. It is a mathematical point on a graph that we can approach infinitely but never touch. It is like the horizon. You see it, you walk toward it, but you never stand on it. This means there is no place in the universe for perfect rest. Silence is an illusion. Even in the deepest, darkest, coldest vacuum of intergalactic space, fields tremble, particles are born and die, and atoms perform their minimal, mandatory dance. We started with the idea that temperature is an illusion of our senses. Now we see that the absence of temperature is also an unattainable abstraction. But if cold is just slowing down, what about the other end of the scale? We said heat is atoms hitting, but the sun doesn't hit us with atoms. Between us and the sun is 93 million miles of void. There is no air, no billiard balls. How then does the sun's heat reach my skin? How does a fire warm us from a distance, even if we don't stick our hand into the flame? So, we stand before a riddle. We found out that heat is colliding atoms, but if you go outside on a sunny day and close your eyes, you feel warmth on your face. This warmth came from the sun. but between your face and the sun lies 150 million kilometers of vacuum. There is no air. There are no billiard balls that could line up in a chain and pass the punch from the sun's surface to your cheek. How does the sun touch you without touching you? The answer lies in the fact that every atom consists of charged particles. We have electrons, and every electron has its entourage, an electric field that extends around it far, far away, theoretically, to the entire universe. Imagine that an electron is a cork in the middle of a huge, calm pond. If the cork hangs motionless, the water is calm. But the sun is very hot. Its atoms and electrons shake with mad fury. What happens when you start yanking the cork up and down sharply? Circles run along the water. Waves, they spread in all directions. The electron does the same thing. When it shakes, it yanks its electric field, and a wave runs along this field, a ripple. This ripple breaks away from the electron and flies through the void at a speed of 300,000 kilometers per second. We call this ripple light, or electromagnetic radiation. Light is simply the echo of a shivering electron. And so this wave flies through space for 8 minutes and finally crashes into your skin. And your skin is full of its own electrons. They were sitting relatively quietly. But then a wave hits. The electric field starts jerking, and it grabs your electrons and starts shaking them. It is a forced dance. The wave forces your skin's electrons to vibrate to the beat of that distant electron on the sun. They start accelerating, hitting neighbors, rocking molecules. And voila, your skin warmed up. The jigga was teleported through the void. It is amazing if you think about it. Light is just a mailman. He picks up the shaking in one place and delivers it to another. And here we come to the most beautiful fact. The frequency of this shaking determines what we name this mailman. If electrons shake lazily and slowly, we call it radio waves. If they shake a bit faster, it's microwaves, the ones that heat your food. If even faster, it's infrared radiation. If they shake very fast, our eye starts to see it. We say, oh, that's red light. Even faster, blue light. And if the shaking becomes hysterical, insane, it's X-rays and gamma rays capable of killing. But in essence, it is all the same thing. It is all field trembling caused by matter trembling. Do you know what this means? It means that everything in the universe glows. Absolutely everything. Look at your hand. Does it seem dark to you? No. Your atoms are shaking, which means your electrons are jerking, which means you are emitting waves. You glow with infrared light like a Christmas tree. It's just that your eyes aren't tuned to this frequency. But a snake would see you in total darkness. A military thermal camera would see you. Even a piece of ice glows. Its atoms shiver, albeit weakly, and send long, faint radio waves of heat into space. The universe is a continuous exchange of light messages. A hot cup of coffee on the table screams infrared light in all directions, giving energy to the walls. The walls whisper back with their weak radiation. A campfire in the woods warms you not with warm air. Warm air flies up into the sky. It warms you with light. You feel the heat on your face because invisible infrared rays bombard your skin, forcing your molecules to dance. We live in an ocean of waves. We constantly receive parcels of energy from everything surrounding us and constantly send them back. This is the great equalizer. The universe tries to equalize temperature not only by collisions, but also by sending light. So when you look at the stars, you don't just see pretty dots. You see how incandescent matter, trillions of kilometers away, shakes so hard that the ripple from this movement reaches your retina and makes molecules inside your brain shake, birthing an image. We are all connected by this web of fields. And now that we have taken temperature apart piece by piece, from molecular punches to quantum trembling and light waves, it is time to put it all back together. It is time to look at that cup of coffee one last time and see in it not a drink, but a symphony. Let's go back to the beginning. Look again at that cup of coffee we started this conversation with an hour ago. It has cooled down. Entropy took its toll. The fastest molecules flew away. The remaining ones calmed down, and now the coffee's temperature has equalized with the room. The drama is over, but now I hope you look at it with completely different eyes. Before, you saw just a brown liquid. Now you should see a miracle. You should see billions of invisible players. You know that even now, in this cooled coffee, a frantic dance is going on. Molecules shove, exchange energy, glow in the infrared range, tossing photons back and forth with the walls of the room. Nothing died. The dance just became a little slower. And therein lies perhaps the deepest lesson physics can give us. We often seek peace. We say, I want everything to calm down. But physics teaches us that true peace is death. It is absolute zero. It is a full stop. Life is not peace. Life is a very specific, very fragile mode of motion. Think about yourself. You are an incredibly complex construction of atoms. Carbon, hydrogen, oxygen, nitrogen. If your body's atoms stopped shivering, you would crumble. If they started shivering too much, like in fire, you would burn. You exist in a tiny, narrow corridor of temperatures, in this golden ratio of chaos. Your body is a machine that masterfully manages this storm. You take energy from food, chemical energy, turn it into ordered movement of muscles and thoughts, and dump the excess chaos, heat, into the environment. You are a temporary island of order in an ocean of entropy. You are riding an avalanche, and this shouldn't be scary. On the contrary, it should bring delight. And when you understand what temperature really is, the world stops being a set of boring objects. A table, a chair, air, water, it all comes alive. It all vibrates. The whole world sings the song of kinetic energy. Thanks for your attention. See you tomorrow.